Welcome back, Chemistry 30. So we'll look at some examples of alkenes and drawing them out. So if we look over here, draw the structure of 2,4-heptadiene. So the thing that stands out here is hept. Hepta, of course, is 7 carbons. So let's draw 7 carbons out. So 1, 2, 3, 4, 5, 6, 7. And we'll number it from left to right. And remember, the number in front. Now, of course, ene indicates that there will be at least one double bond. We have the prefix di, which means there's going to be 2 double bonds. And those are going to be positions 2 and 4. So position 2, there's a double bond. And starting at position 4, there's a double bond. Okay, so there's no other branch chains. I don't see any methyl or ethyl, so it's just simply this. And now I just have to worry about drawing the extra hydrogen. So this carbon is bonded to this carbon, so it needs 3 more hydrogens. This carbon is bonded to 1, 2, 3 things, so it needs 1 hydrogen. Same thing with this one, 1, 2, 3, needs 1 hydrogen. This carbon, 1, 2, 3, needs 1 hydrogen. This one needs 1 hydrogen. This one, 1, 2, so it needs 2 hydrogens. And this one here, 1, so it needs 3 more hydrogens. So there we go. That's 2,4-heptadiene. So that di, tri, or tetra comes before the ene, indicating how many of the double bonds we need to include there. Here's another heptene. So I'll draw 7 carbons. 4, 5, 6, 7, and I'll number them from left to right. And there's no di here, and we only see a number 2 here, so that means there's a double bond at number 2. And then at 4, 6, I have 2 methyls, so 4 and 6, I have methyl groups. So that is how those go on. Now we just have to worry about the H's. This carbon is bonded to 1 carbon, so 3 H's I need. This carbon, 1, 2, 3, so it needs 1 more bond, H. 1, 2, 3, 1 more bond. 1, 2, 3, 1 more H. 1, 2, so 2 more. 1, 2, 3, so 1 more, and 1, so I need 3 H's there. And there we go. This one, we can see a double bond. Remember, so this is showing H's just branching off as opposed to having this end piece looking like this. It's showing the H's going off. Be careful, just worry about the carbons. So don't fall in the trap of circling this too. We just worry about the carbons. That's the biggest chain I can make. It is 4. And again, I start numbering in the direction that gets me to the double bond the quickest. So 1, 2, 3, 4. And 1, 2, 3, 4 carbons is bute. There's only 1 double bond, so it's just butene. And what else do I have going on? I have at, position 3, I have methyl and methyl. Methyl, methyl. So at 3, now I have to say 3 twice because there's 1 at 3 and 1 at 3. So you have to say that twice and then have the di. So these should match. The number of numbers here should match the prefix I use here. So 3, 3, dimethyl. I'm going to run out of room here, so I need to move these over just a little bit. So it's 3, 3 dash dimethyl. And then at position 1 is where the double bond starts, 1 butene. So 3, 3 dimethyl, 1 butene. All right, continuing on to the next page. So 4-methyl-2-pentene. Pent is 5, so 1, 2, 3, 4, 5. And ene indicates a double bond. There's no prefix here, so it's only going to be 1 double bond at position 2. So if I number it from left to right, position 2, there's a double bond. And then at position 4, I have a methyl group. So 4-methyl, 2-pentene. Just have to fill in the hydrogen. So this carbon is bonded to this one. Needs 3 more. This carbon, 1, 2, 3, so it needs 1 H. This carbon, 1, 2, 3, needs 1 H. This carbon, 1, 2, 3, needs 1. And this carbon is bonded to 1, so I need 3 over there. So you may want to pause the video and just kind of continue on here. At the very bottom of the page, we do run into a trans geometric isomer, and we're going to add another one here, a cis version too, so we can see how that works. We'll add cis 4-octene. So you may want to pause the video and just get a jump start and see if you can do these. All right, so hopefully you had a chance to pause the video and try it. Octene, so that's 8. 1, 2, 3, 4, 5, 6, 7, 8. There is a double bond, but there's no prefix here, so it must just be one of them at position 3. 4, 5, 6, 7, 8. And then we have methyls. See, the prefix tri indicates that there's 3 of them, so there's the location of the 3 methyl groups. There's 2 of them at position 2, 2, 2, 6. 2, 2, 6. And of course I could have drawn this below, it doesn't matter, because there's rotation around single bonds. Double bonds, however, there isn't. This carbon, 1, 2, 3, 4, it doesn't need an H. This carbon, 1, 2, 3, needs 1. 1, 2, 3, needs 1. 1, 2, needs 2. This carbon, 1, 2, 3, so it needs a single H. This one needs 2, and this one needs 3. There we go. This one, pent. That's 5, of course. 3, 4, 5. And notice there's a di there. So at positions 1 and 3, there will be double bonds. So 1 is where the start of the first double bond is, and then 3 is the start of the next double bond. And that's it. There's no methyl or ethyls attached, so we just have to add the H's. So this carbon needs 2 H's because it has 2 bonds. This carbon needs 1 H because it has 1, 2, 3 bonds. Same thing with this one. This carbon has 3 bonds, so it needs only 1 H. And this end carbon, which is only bonded to this carbon, needs 3. All right. So looking at the geometric isomer now. The easiest way to do this is to make it 2 carbons with a double bond. Okay? Hex, that means 6 carbons in total. So I'm going to branch off and do 2 more in this direction and 2 more in this direction. Trans means opposite side. So I'll do it one way. I'll show it as carbons going up in this direction and down in this direction. And then what's going on over here? Just an H and an H. I could have drawn this other way. I could have these carbons going down and this one going up, as long as they're on opposite sides. Opposite sides of the double bond, it'll be a trans version. This carbon here is bonded to 2 things, so it needs 2 H's, and this carbon here needs 3. And same thing on this side. This carbon is good, 1, 2, 3, 4. This carbon's good, 1, 2, 3, 4. So there we go. Trans 3-hexene. Let's look at this one. So again, double bond carbons, and then octene, I need 3 more in either direction. Cis means same side, so I could draw them both going up, or I could have drawn them both going down. It doesn't matter. 1, 2, 3, 4, 5, 6, 7, 8. So there we go. And so this carbon here needs an extra H. So I could have drawn them both going up like I did there. Same side, or opposite, or going up, or same side going down. Then just filling in the H's, need 2 there, need 2 here, and need 3 over there. All right, so that's how you do the cis-trans isomers. Okay, and the last example here, pentene, but it's a cyclo. a cyclic 5-ring structure. 1, 2, 3, 4, 5. Oh, goodness. There we go. So it's a pentagon shape, right? And we assume that there's a carbon at each of those vertices or points. And again, we don't write the number of the double bond because we assume it is in between position 1 and 2. So we make it at position in between 1 and 2. Also at position 1, we have a methyl group. And at position 3, we have an ethyl group, which is 2 carbons. So let's see here. This carbon is bonded to 2 things, so it needs 2H. This carbon is bonded to 1 other carbon, so it needs 3. There we go. So those are the cyclic structures. Again, double bond is in between 2 and 1. And then we can go from there. Properties and uses of alkenes. Like alkanes, alkenes are nonpolar and therefore have low solubility in water as well as relative low melting and boiling points. However, alkenes are more reactive than alkanes because that second covalent bond, so that double bond gives more electrons. So instead of having 2 electrons, there's now 4. So that area tends to be a little more reactive than, let's say, a single bond. Reactants that attract electrons can pull those electrons away from the double bond. Several alkenes occur naturally in living organisms. For example, ethene, that's 2 carbons, are produced naturally by plants as a hormone. It causes fruit to ripen and plays a part in causing leaves to fall from deciduous trees in preparation for winter. Tomatoes and other fruit can be ripened artificially by using ethene, so it's kind of an aging agent. Ethene also is the starting material for the synthesis of the plastic polyethylene, which is used to manufacture many products, including plastic bags and milk jugs. Natural rubber is another polymerized alkene. Other alkenes are responsible for the scents of lemons, limes, and pine trees. So there we go. So we went through the naming and some uses and drawing the structures. So you should be able to do the assignment now. We'll see you again.